So if you take a picture of like your coffee mug sitting on your desk and you run it through some software, boom, you get a perfect digital reality.
Right, yeah, a one-to-one 3D model.
Exactly. The shape, the color, the position, it is all captured flawlessly. But if you step into a massive industrial refinery and point that exact same camera at a tangle of, 1,000 steel pipes and valves and gauges, that digital mirror just completely shatters.
Oh, it falls apart entirely.
It really does. But today is August 3, 2026, and we are looking at a brand new technical release from EON AI Ventures, and they are claiming that they finally figured out how to glue that mirror back together.
Which is a huge claim, by the way.
Yeah. So our mission for this deep dive is to explore their new framework. We're looking at how they take ordinary sight photographs of these incredibly complex industrial spaces and turn them into accurate, fully named 3D models. And they're doing this at an industrial scale.
And, this matters for you, the listener, because critical thinking in a world of constant AI hype means we can't just accept that a new tech works. We have to examine exactly how it proves its own accuracy.
Right, like show your work.
Exactly.
Yeah.
Because anyone who works in facility engineering or industrial maintenance knows this is, frankly, one of the most notoriously stubborn problems out there.
Yeah, you called it a known hurdle earlier. EON calls it the wall in their press release.
Yeah, the wall. Because, like you said with the coffee mug, making a 3D model of a single isolated pump from photos works beautifully today.
The tech is there.
It is. But when you apply that exact same photogrammetry tech to a sprawling manufacturing floor with dozens or hundreds of connected components, it just breaks down.
So what does that breakdown actually look like?
Well, the current systems just lose parts. Small valves get missed, things get misidentified, and crucially, you get a 3D model that has absolutely no connection to the plant's actual operating systems.
Okay, let's unpack this a little. It sounds a lot like using portrait mode on your smartphone.
Oh, that's a good analogy.
Right, like it's perfect for one face, the background blurs out, the face is sharp, but if you point portrait mode at a massive crowd at a concert, it just sort of panics. It blurs everyone together or, tags the wrong people.
That is exactly what happens. The spatial reasoning of the software just gets completely overwhelmed by the density.
So small bleed valves get missed because they blend into the background pipes.
Yeah. Or gauges are totally ignored.
Yeah.
And even if this system does manage to build a nice 3D shape of a valve, it gives it the wrong name.
Which means nothing gets built with a name that the spare parts system actually recognizes.
Right. And you're left with a very pretty, very expensive 3D picture of a plant that doesn't actually help a maintenance worker do their job.
But wait, why hasn't a better camera solved this by now? I mean, we have drone cameras, we have LiDAR, we have insane megapixel resolution in our pockets.
Well, that's the thing. EON's foundational realization here is that a better camera isn't the fix.
It's not.
No, because it's not an optical problem. It's actually a categorization problem.
Okay, how so?
So historically, systems have tried to figure out a component's position, like where it sits in space, and its identity, what it actually is, at the exact same time.
Oh, I see. Doing both jobs at once.
Right. But EON decided to completely split those two jobs apart. They treat building the physical geometry and then naming the parts as two entirely separate pipelines.
So if we are decoupling the where from the what, how do they establish where a thing is in a crowded plant if they don't even know what they're looking at yet?
They use a strictly enforced spatial checking system. They call it the 4-view rule.
The 4-view rule. Okay, break that down for us.
So instead of trying to understand the whole image at once, the system takes a high-resolution pixel crop of a suspected component from one photo.
Just a tiny square of the image.
Exactly. And then it mathematically checks that exact crop against other camera views of that same area.
But wait, translating a flat 2D crop into a verified 3D coordinate, that seems like it would require some heavy geometric math.
Oh, it does. The progression of how they confirm a point in space is actually super fascinating. So one view gives you a direction.
Like a ray shooting out from the camera lens.
Yeah, exactly. Then two views give you a crossing.
So two rays intersecting in space, which makes a line.
Right. Then three views give you a point. A precise triangulation.
Which, I mean, that sounds like enough. Triangulation is how GPS works, right? Why do they need a fourth view?
Because in a dense environment, think about a room full of identical gray pipes crossing over each other. Three views can easily give you a false positive.
Oh, like two pipes just happen to line up perfectly in the photo and trick the math?
Yes, that is exactly why they mandate 4 views. 4 views give you that precise point in space, plus an independent mathematical vote.
A vote.
Yeah, a vote to confirm it. So if the AI mistakenly draws a bounding box around a weird shadow, that error is caught immediately because that fourth view acts as a tiebreaker.
Wow, okay, so it stops false positives dead in their tracks.
Exactly. It guarantees that a wrong box is definitively identified as an error rather than just suspected.
But I want to push back on this a bit because the source material brings up a really tricky scenario. The identical twin problem.
Oh yeah, this happens all the time in industrial sites.
Right, you have multiple identical valves sitting side by side on a skid down to the exact same rust spots.
Yeah, they look exactly the same.
So if the image inside the crop is not visually distinct at all, how does the system not just merge those two twin valves into one giant blob in the 3D space?
Well, EON solves this by looking at the background context of the images.
The background, not the valve itself.
Right. Because a cropped image of the first valve will not mathematically corroborate against a camera view that only contains the second valve.
Oh, I get it. The structural beams behind it or the distance to the floor.
Exactly. The intersecting shadows, the pipes behind it, the spatial geometry of the surrounding space won't match up.
So the space around the twin gives away its location, even if the valve itself is a perfect clone.
You got it. And because this positioning math doesn't wait around for the naming process, the geometry can be mapped out and locked in while the identity of the valves is still a total mystery.
So they build the physical reality first and label it later.
Yes, whereas competitors usually hold the geometry back until they can figure out the name.
Okay, so now you've got a million unlabeled gray boxes perfectly plotted in 3D space, which is a cool parlor trick, but completely useless to a guy with an emergency work order trying to fix valve 402.
Right, it doesn't help at all yet.
So here's where it gets really interesting. How does the system transition from knowing something is here to knowing this is definitely valve 402?
This is what EON calls the sophisticated half of the build. They bring together 4 independent sources that honestly have never spoken to each other before.
4 sources. Okay, let's go through them. The first is the engineering drawing, the P&ID.
Right, the piping and instrumentation diagram.
But any facility engineer will tell you that a P&ID is just a schematic, right? Like a subway map. A valve in the top right corner of the paper might actually be bolted to the floor in the bottom left of the real plant.
Which is exactly why EON's system is super careful with the P&ID. The release states clearly that the drawing is used only for the inventory of tags and the order of connections.
So just the topology.
Yeah, just what should exist and what connects to what. It is never used to determine physical position.
Because paper drawings from 30 years ago are notoriously unreliable for physical locations.
Oh, totally unreliable.
So we need physical grounding, which brings us to the second source, the photographs.
Right. The photos provide the proof of existence. They show position, and they let the AI match the visual shape against a library of 363 equipment classes.
So the AI looks at the shape and says, I am statistically confident this object is a valve, not a pump.
Exactly. And then we hit the third source, which is where things get really wild.
The nameplates.
The physical nameplates bolted directly to the equipment.
The little metal tags with the serial numbers. But wait, AI reading text from images, optical character recognition that's been around forever. Why is EON's way of reading plates a breakthrough?
Because of the very specific 2-stage process they use to stop the AI from hallucinating.
Hallucinating, like making things up.
Yeah. In industrial photos, nameplates are usually tiny, covered in grime, poorly lit. If you feed a blurry image to a modern AI, it wants to find a word so badly that it will literally invent characters out of pixel noise.
It just guesses to please you.
Right. So to stop that, EON's system first uses low-resolution copies of the photos just to find where a plate is.
Just hunting for text-bearing metal.
Exactly. Then it stops. It goes back to the massive full-resolution original photograph, recrops that tiny specific spot, and only then does it actually try to transcribe the letters.
Wow. Okay, so by forcing the AI to only read the highest fidelity crop, it removes the blur that causes those hallucinations.
It creates a strict firewall against AI guesswork.
Yeah.
And the press release highlights a huge philosophical shift here.
Yeah, I noticed this part too.
A nameplate bolted to a part is the only statement on an industrial skid that is not an opinion.
It's documentary evidence.
It is a physical fact.
That is such a huge shift in thinking, and that leads right into the fourth source, which kind of acts like the ultimate judge.
The manufacturer's published catalog.
Right.
Once the system reads the manufacturer name and model from that metal plate, it goes straight to the web and retrieves the actual manufacturer's catalog.
And it does this just once per manufacturer, right?
Yeah, to make sure it's the real technical publication, not some third-party distributor summary.
So to recap, the drawing gives the intent, the photo gives the class, the nameplate gives the serial number, and the catalog gives the absolute ground truth.
You've got it.
Let's actually look at a specific example of this from the text because it really clarifies things. The ballon valve dispute.
Oh, this is a great real-world example from their test skid.
So they were doing a test run and they hit a direct contradiction.
Yeah. Source number 1, the highly regulated engineering drawing, explicitly said a certain component was a gate valve.
But source number 2, the AI looking at the photo said, that looks like a ball valve.
Right. So the paperwork says gate, the photo says ball. In older systems, this is where the software just throws its hands up, throws an error flag, and begs a human to come fix it.
But EON resolves it without a human. How?
It escalates to sources 3 and 4. It zooms in on the physical equipment, does that two-stage transcription, and it reads the word ballon cast right into the metal handle.
BALON.
Right. Then it pulls the Ballon Corporation's published catalog.
And what did the catalog say?
The catalog proved that Ballon Corporation makes ball valves, check valves, and needle valves. They do not manufacture gate valves.
Wow. So the manufacturer's own catalog proved it was literally impossible for that object to be what the blueprint claimed it was?
The manufacturer contradicted the site's own engineering drawing.
Mm-hmm.
And they resolved 3 out of 5 conflicts on this exact test skid using that exact method.
The paper was wrong and the forged metal was right.
Exactly.
But, reading about these catalogs in the source, I did have a moment of skepticism.
Oh, what caught your eye?
The text mentions that these catalogs provide, quote, better pictures than the field ever produced.
Ah, yes.
Now, we know plant photos are usually dark or half the pump is blocked by a pipe. But catalog photos are gorgeous, studio-lit perfection.
Right.
Are they just quietly swapping out bad field photos and replacing them with nice, shiny catalog pictures to make the 3D model look better for the client?
It's a fair question, but EON is very strict about this. They explicitly forbid that kind of silent swapping.
Okay, good.
The actual real-world field views are always kept, and they are always shown first as evidence, even if they are terrible.
Right, because if you hide a bad photo, you're hiding reality.
Exactly. If a view is missing, it is explicitly stated as missing. They never just backfill it with a catalog image to cover up a gap.
That's crucial for the integrity of the evidence.
But actually, the catalog serves a third job that is way more genius than just providing a clean picture. It acts as a ruler.
A ruler? Wait, explain that.
Well, think about a standard 2D photograph. It has 0 sense of scale.
Right. If you show me a picture of a pipe against a white wall, I don't know if it's 2 inches wide or 2 feet wide.
Exactly. Normally, to get a metric scale from photos, engineers have to do this insanely complex math called a photogrammetric, solve calculating focal lengths and lens distortions, or they have to buy expensive laser scanners.
So how does EON skip all that?
Because of the datasheet. The manufacturer's datasheet lists the exact millimeter dimensions of that part.
Oh.
Yeah. So once the system definitively knows this is valve X, it pulls the millimeters from the catalog, and suddenly it has a measuring stick baked right into the pixel data.
That is so smart. If the catalog says the valve is exactly 150 millimeters long, it can use that 150 millimeters to measure the pipe next to it.
Or the distance to the floor.
Yeah.
Everything in that photo frame now has a metric scale, without lasers, without survey instruments.
This is from ordinary photos. Okay, so they have the geometry mapped, the naming verified, the scale figured out. How is all this data actually stored?
The release outlines 3 interconnected libraries that EON is building.
Okay.
First is the 3D library, which is just the looks, the physical geometry. Second is smart components, which is the function, what the part does, its flow rates, all that.
And then the third one?
The third one's the big one, the field album.
The field album.
Yeah, this acts as the system's memory. It records every single actual field sighting tied to those real datasheet dimensions.
And this creates that compounding knowledge effect, right?
Exactly.
There's actually a quote in the source from EON founder Dan Lajerskar. He says, "The field album is the piece I would build a decade around."
Yeah, and you can see why. By accumulating this verified data, when they go scan their 50th industrial site, it's going to build so much faster than their 5th site did.
Even if the photos at the 50th site are terrible.
Right, because the system already knows what that specific pressure valve looks like in the real world from a past job. Competitors can't just write a better algorithm to beat that. They're fundamentally behind on years of actual field data.
Okay, this all sounds incredibly powerful, but we need to ground the hype a little bit.
Always a good idea.
If we look strictly at the data in the press release, What does this actually mean in reality right now? What have they actually built versus what is just a planned feature?
The release is actually remarkably disciplined about its numbers. They list the exact metrics from a test run on July 27th and 28th, 2026.
Okay, let's hear the numbers.
First off, they did not scan a whole refinery.
Right, no sprawling city of pipes yet.
No, they scanned exactly one process skid. The input was tiny, just 21 photographs and exactly one drawing sheet.
Wow, just 21 photos. That's really small.
Very small. But on that skid, they found 32 components. They successfully located 30 of them across the 4 views with 0 failures.
0 failures on the location.
Yep. And they successfully transcribed 28 nameplates. And, as we mentioned earlier, resolved 3 out of 5 drawing conflicts using the catalog.
Those are very strict factual numbers.
They are. But to your point about what's built versus planned, features like that multi-site compounding effect of the field album or the camera pose solving for global GPS coordinates. Those are designed but not yet built.
Okay, that's really important to note. Everything in the test was operational, but the bigger ecosystem is still on the roadmap.
Exactly.
So zooming out beyond just oil and gas, this framework isn't limited to industrial pipes, is it?
Not at all. The AI doesn't care if it's looking at a steel pipe or a medical device. The class library is just a swappable input.
So you could swap out the industrial library for, say, a hospital library.
Oh, absolutely. Think about a huge hospital with hundreds of visually identical ventilators moving from room to room.
Where the paperwork is constantly lagging behind reality.
Right. Or aviation maintenance dealing with thousands of identical aircraft parts. Or hyperscale data centers with endless rows of identical server racks.
Anywhere you have visually identical equipment and paperwork that is drifting from reality.
Which is pretty much every major industry.
Which brings us to the core of this whole thing. Confidence in data. Why should a safety director trust this AI over their own decades-old blueprints?
Because of how it scores its own work. It gives a confidence score based on physical documentary evidence.
Like the bolted nameplate?
Yes, not an AI black box guess. And if the blueprint and the photo disagree, it doesn't average them out into a lie. It shows you both, side by side, with the high-resolution photo that settles the dispute.
It's just strict adherence to evidence.
Exactly. That's what lets an engineer confidently dispatch a technician to work on high-voltage equipment based on a digital model.
Right. It eliminates the guesswork, which leaves us, really, with a pretty massive thought to ponder. If a state-of-the-art AI system can objectively prove that highly regulated, meticulously drafted engineering drawings are routinely contradicted by the very nameplates bolted to the machinery.
It makes you wonder.
It does. How much of our entire global infrastructure, from the hospital you might visit next week to the massive data center streaming this audio to you right now, is operating on paperwork that is fundamentally out of sync with physical reality?
A very sobering thought.
Definitely something to mull over.
Thanks for joining us on this deep dive.